All right, so continuing along the idea of approximating the area under a curve with these Riemann sums, we're asked to do two different things with this area approximation. And letter A should be quick for us, but B is an important idea that we want to consider in the future when deciding what the best way is to evaluate the area under the curve. So let's let A be this area here, and that's the area of the region that lies under the curve. F of x equals e to the negative x. So that's what this function is that I've sketched, e to the negative x. Between x equals 0 and x equals 2. So we've got that there. Using right endpoints, find an expression for a as a limit. Do not evaluate the limit. All right, so let's use what we came up with in the last video and what we've learned over the past two lessons to evaluate a here. We'll do all of our work for a in green. So a. We're given that the function is e to the negative x, and we've got our first endpoint of our domain as a equals 0, and b would be 2. That's the right-hand end of our domain for this function. And so we want to know what is the change in x that we're going to be using here. So in order to calculate that, we do a little calculation, which is a formula we used last time, that just says take b, subtract a, and divide that by the number of slices we want to take of this region, because we're going to be sketching rectangles, right? So this ends up being 2 over n. So that's what we're going to consider to be our delta x. And if I sketch this in, remember it says we're using right endpoints. We've got maybe here is your x1, right? So that's a rectangle that looks like this. And then we've got an x2, and so on. And so what we've decided here now is that this distance between each of these is 2 over n. That's what that means, right? That's delta x. It's that same distance every single time. And this will continue. We've got our x3, and then sometime later we've got more x intervals all the way up to our final interval, which would be x sub n, but that's 2. Okay, so our intervals happen every 2 over n times. We don't know what n is because we don't know how many chunks we're taking here. Remember, we're going to take that limit as n approaches infinity. So when we're building our rectangles here, we want to consider what are the areas of these rectangles going to be. What's going to be the area of this first rectangle? Well, the area of the first rectangle, just doing some work off to the side, is going to be base times the height of that rectangle. The base of that rectangle is delta x, and the height of that rectangle is f of x1. Just noticing that that's how tall this rectangle is. It's wherever this x value intersects with the function. So that would be the height of that rectangle, and then I could even rewrite delta x as 2 over n, because we figured out that that's what 2 over n is. So that would just be our first rectangle, right? And then we would continue this process over and over and over. And so what we did yesterday, or in our previous lesson, is we turned this into a sum. Because we're not just adding the first and second rectangle, we're adding an infinite number of these. So the sum of the areas of the right-hand rectangles is going to be the sum of all of our rectangles that have this area created by f of x sub I times delta x. And that's where we just came up with that formula. We're going to replace that with a delta x from when I is 1 all the way to when I is whatever n turns out to be. Okay, so then I can replace these values with the values that we've calculated them to be. So this is the sum from when I equals 1 to when I equals n. Again, we don't know how many of these rectangles we're going to have, of f of, and if I consider what x1 would be, it would be 2 over n times that number, right? This would be 2 over n times 1, and this is another 2 over n, and then this would be a third 2 over n. So I could rewrite f of x1 as f of 2 over n times 1, because it's the first of the rectangles that we're going to build. So I'll rewrite this here as f of 2 over n times I, leaving this wide open for any rectangle that I would want to adjust the height of times delta x, which is 2 over n. So this is an expression that I could use to evaluate the sum of these right-hand rectangles. And consider that we know what the function is, so I would be able to rewrite f of 2i over n as e to the negative 2i over n, because that is the actual function, times 2 over n. And I could rewrite that in another nice way if I really wanted to. So I equals 1 to n. Now let's consider how this would be different if we used midpoints. So I'm going to use yellow to do our midpoint calculations. All right, so we haven't done this yet, but what we're going to do now is instead of using a right side or a left side of our rectangles, we're going to use the center of the rectangles to represent the height of the rectangle. So I've just drawn over black over all the green, so don't mind the sections of weird colored chalkboard here. We're asked to cut this up into 4 subintervals, so I'm just going to actually draw those in. We've got our 4 subintervals now. I could call this x1, but we know exactly where that would be. That would be at 0.5, right? Because that's halfway to x2, which would be 1, and x3, which would be 1.5. So we've got the locations of each of these places. We're going to create rectangles, but I'm not going to draw my rectangle until the right-hand side hits the function. I'm going to draw my rectangle until the center of that rectangle hits the function. So that rectangle would look like this. And then I'll draw in the next 3 rectangles. So this is what our 4 rectangles would look like. And you can see maybe where the benefits might be of doing something like this, because now part of our rectangle is over approximating and the other part is under approximating. So we might be splitting the difference here and getting really, really close to the actual correct value. We'll see. Hopefully these get a little bit more accurate. So when I calculate the areas of these rectangles, they're a little bit different now. I'm not able to use my x1 as the height of the rectangle or x2 on either side. I have to come up with new values here. So we're going to adjust these values, and I'm going to call this x1 with a little star that's saying that this is our adjusted x1 value, and it's halfway between 0 and the other x1 value. So this would be at 0.25, right? Because it's halfway between 0 and 0.5. And then we've got another one here. I would call this maybe x2 star, and that's halfway between 0.5 and 1, so 0.75. I've got one here, which would be, let's say, x3 star, and that's going to be halfway between 1 and 1.5. And then finally I've got another one of these, which is halfway between 1.5 and 2. And so those are the numbers that we're going to want to use when evaluating the height of the rectangle. Because if I say I want the area of this first section, well, what's that area going to be? It's the base, and the base is our change in x times the height, which is f of xi star. Well, in this case, for A1, what is delta x? Well, our change in x turns out here to be 0.5, because if I do a little delta x calculation, that's 2 minus 0 divided by 4 subintervals, 0.5. So that's 0.5 times f of 0.25. And that's how I'll get the area of just that first rectangle. All right, and then I could do the same thing to find the second rectangle. That would be 0.5 times f of 0.75, and so on. So what I want to do is approximate the area under this curve to be the midpoints. And there are 4 of them, of these 4 rectangles. And so that's just the sum of this function, f of xi star, right, midpoints, and we just use that to denote that it's an adjusted value on the x-axis, times delta x. And we can start filling in the things we know about this function now. And I can say from 1 to 4 because I know how many subintervals I have now. And so we already started this calculation here. We've got our area 1. Our first rectangle was delta x, which was 0.5, times f of 0.25 plus 0.5 times f of, this is our second rectangle, plus our third rectangle, which has a base of 0.5 and a height of whatever f of 1.25 is, plus one more rectangle, which has a base of 0.5 and a height of f of 1.75. And so we could actually evaluate these because we have the function, right? We have the equation, which is e to the negative x. So I'm just going to write the next row here, which is me plugging in those values to the function. So now I would use a calculator and actually evaluate this if you wanted to factor out those 0.5s, because maybe you've noticed that these all have a 0.5, so to make the page look a little nicer, you could factor out 0.5s. You could do that. When I plug this into a calculator, I'm going to get approximately 0.8557, which is the approximate area under the curve. But remember, that contains some over approximations and some under approximations. But maybe the fact that we used midpoints compensated for those over and under approximations in a better way than the right and left hand sides of rectangles did.